Hello students, welcome. Previously, Form 4, Topic 2, Lesson 7, we were dealing with molar heat of neutralization. Today, Lesson 8, we are going to do Hess's law. Let us start first of all by stating what Hess's law is. We say Hess's law states that the energy change in converting reactants to product is the same, regardless of the route by which the chemical change occurs. So during the exam, if you are told state the Hess's law, that is the answer. So we go straight to the examples. Example 1, we are told the thermochemical equation for the combustion of carbon in bracket graphite and carbon 2 oxide are as follows. So here we have carbon reacting with the oxygen, giving us carbon dioxide, and this is the standard heat of combustion of carbon, which is negative 393 kilojoules per mole. And here we're having carbon 2 oxide reacting with the half of oxygen, giving us carbon dioxide, and this is the standard heat of combustion of carbon 2 oxide gas, which is negative 283 kilojoules per mole. So, part A of the question, we are told use the information provided to draw an energy cycle diagram. So here we are supposed to draw the energy cycle diagram, and we are given two equations only. That's carbon reacting with oxygen, giving us carbon dioxide, and here we are having carbon 2 oxide reacting with the half of oxygen gas, giving us carbon dioxide. So to start, when you are told to draw the energy cycle diagram, you are supposed to know something called, first of all, standard enthalpy of formation. What is standard enthalpy of formation? This is the heat change when 1 mole of a substance is formed from its constituent elements in their standard state. Like in our case, we are supposed to have the formation of carbon 2 oxide for that reaction, the reaction that produces carbon 2 oxide. So the elements that form carbon 2 oxide are two. That's carbon, which is solid, plus oxygen, which is a gas, giving us now carbon 2 oxide gas. Okay, so this equation is not balanced. Then for us to balance, we are going to put half of oxygen there, because we cannot balance by putting 2 here and by putting 2 here, because that's not the standard enthalpy of formation of carbon 2 oxide. Because we are told when 1 mole of a substance is formed from its constituent elements. So here carbon 2 oxide is 1 mole. So if you put 2 here, so that's not mole of that substance. It will be 2 mole. So if you're having here 1 mole, you have to balance the reactants even by using fractions. You're supposed to balance it. Then thereafter, we have this equation that's carbon reacting with oxygen, giving us carbon dioxide. So we can have an arrow there. Then we are going to say balance oxygen, which is a gas, will give us carbon dioxide, which is a gas. So on the other side again, we have carbon 2 oxide gas. In our case, it is here. If it reacts with half of oxygen gas, we are still going to get carbon dioxide. That means we can have another arrow coming from carbon 2 oxide plus half of oxygen gas, which can give us now carbon dioxide gas. So what we have drawn now is known as energy cycle diagram. Energy cycle diagram. That's how you are supposed to draw energy cycle diagram. Then number 2, part B of part A, Romeo 2, we are told an energy level diagram. We have drawn energy level on that side of endothermic and exothermic reactions. First of all, we are supposed to draw our axis. That means the y-axis and the x-axis. So we are having our axis. Okay. So we said on the x-axis, this side, we are going to write reaction path. We are going to start with the reaction path. And on this other side, we are going to write energy in kilojoules. Energy in kilojoules, kJ. Okay, so you can draw an energy level diagram by first of all knowing heat of formation of or the reaction for the formation of carbon 2 oxide. If you know that, we are going to have up, because that is also an exothermic reaction. And we are told the reactants are having a higher energy content compared to the products. So we are going to have carbon, which is solid, reacting with a half of oxygen gas, giving us carbon 2 oxide. So that means the product will be carbon 2 oxide. It is supposed to come down. So we are going to have carbon dioxide here. So we have carbon dioxide gas. I mean carbon 2 oxide, sorry. We are going to get carbon 2 oxide gas. So if that carbon 2 oxide gas reacts with oxygen gas, if it reacts with the half of oxygen gas, that means what we are going to get there as a product will be carbon dioxide. So we are going to get something called carbon dioxide. And carbon dioxide is a gas. So there's another reaction that produces carbon dioxide, and that's when carbon reacts with oxygen. That's the carbon. So if I can have an arrow there to come to this side, it can react with oxygen gas, giving you still carbon dioxide. So what I have drawn here will be an energy level diagram for that thermochemical equations given. Because up we are told that use the information provided to draw Romeo 1, I mean an energy cycle diagram, Romeo 2, an energy level diagram. So if you have energy cycle diagram, you can use that one even to draw the energy level diagram. How are you going to do that? You only check your energy cycle diagram. The first equation, that's the heat of formation, or the reaction for the formation of carbon 2 oxide, will be your first equation when you are dealing with the energy level diagram. Then that means the second, that's the carbon 2 oxide reacting with half oxygen gas, given you carbon dioxide, will be the second equation there. Then that means that equation where we have carbon reacting with oxygen, given you carbon dioxide, will be this one that you have here. So that will be for the information. Okay, but B of the question, we are told use the energy cycle and energy level diagram drawn in A to determine the enthalpy of formation of carbon 2 oxide. So they want for us to use these two diagrams and try to calculate the enthalpy of formation of carbon 2 oxide. That enthalpy of formation of carbon 2 oxide is this one. They are looking for this enthalpy of formation. Okay, to use this one, they have already given us carbon to carbon dioxide here. So that means we have the enthalpy change here. If we just write enthalpy change 1, we are told this is 393 kilojoules per mole. So this other side, carbon 2 oxide reacting with half oxygen gas, we are given negative 283 kilojoules per mole. So if we take this one as enthalpy change 1 and this one to be enthalpy change 2, and we take enthalpy change 3 here, what has Hess's law states? We said Hess's law states that the energy change in converting reactants to product is the same regardless of the route by which the chemical change occurs. So in our case, we have two routes of obtaining carbon dioxide. One route is now coming from carbon reacting with oxygen, giving you carbon dioxide. The other route is having carbon reacting with half of oxygen gas, giving you carbon 2 oxide. Then taking that carbon 2 oxide reacting with half mole of oxygen gas will give you now carbon dioxide. So there are two routes. So that means to write the expression, the answer will be enthalpy change 1 will be equal to enthalpy change 2 plus enthalpy change 3. That will be the expression. So I can write enthalpy change 1 will be equal to enthalpy change 2 plus enthalpy change 3. Okay, using your figures, you can just try to substitute, or you can make enthalpy change 2 to be your subject formula. Okay, let's just try to have our values. Enthalpy change 1 is negative 393. So we're going to have negative 393. This will be equal to enthalpy change 2. We don't know because it's the one that we are looking for, plus. What about enthalpy change 3? Enthalpy change 3 here, we have negative 283. So we are going to say minus 283. So that means for me to get enthalpy change 2, if you want to get enthalpy change 2, it will be equal to negative 393, and this one will go on the other side and it changes the sign, plus 283. So enthalpy change 2, which is the enthalpy for, or the heat change for the formation of carbon 2 oxide, will be, if you put it in the calculator, you are going to get negative 110 So the unit will be kilojoules per mole. That will be the answer. Okay,